This is the third and the last part of week one's lecture. First, we talk about the first kind of software engineering activities being uh, the development process. Next is the quality assurance. It makes sure that the activities are performed properly and that also the software artifacts produced by all the activities right here are good. They meet the software requirements and the quality standard. The word artifacts, you can think of it as artificial product, something that is man-made. That is called artifacts. So this term we'll see it quite a bit, artifacts. So you can think of it as software products, but not products for the users, but the products inside a software project, some sort of internal products. For example, a document, a design document could be an artifact, or a file, a program, okay, because a system we build may have hundreds of programs actually. So they can also be called artifacts. This slide shows the software quality assurance activities. After we've done some work, we need to verify that it's done properly. So these activities shown here are using the waterfall process. Okay, waterfall process start with requirements analysis, and then that means we identified if we give a little bit of details of the requirements. So we find out in some details what the user needs, and then we design the software. In design, it probably means we identified a number of big components, and also we don't go into the coding yet, but the components, what components are needed, and how the components are related would be the work of software design. And then for each small component, we code it and we unit test it. Unit test means we look at each small component and we just make sure that this small component works properly by itself. So a unit could be a class, very commonly, like the unit would be a class. And we integrate them together. So after integration, we do some integration testing. So this is different from unit testing. Unit testing just tests a component by itself. Integration testing tests a component being fit with another component. So they are now different components are connected, and we want to see they're still working correctly. And once we integrate all the components in the whole system, we're ready to do acceptance testing, sometimes called user acceptance testing. UAT is commonly what they're called. And then we later on go into the maintenance mode. Right-hand side, you can see the artifacts or the product of these activities. For example, after analysis, we would create an SRS, software requirements specification. After software design, we would probably have some diagrams, some design documents. Coding will have lots of files. Okay, if it's a C++ project, we would have .cpp files, and if it's Java, then we'll have lots of .java file, and so on. And after integration, we now have the software. And once it passed the acceptance testing, we would deploy the software in the user's environment. Because initially, all those previous coding stuff may have generally happen in the programmer's environment, but later on it will be deployed to the production environment or the user's environment. Okay. So this is right hand side shows different kind of validation. Static validation. Static means you don't have to execute the code to validate it. For example, just by reading the design, or maybe some other programmers will learn inspection, something called inspection. One programmer may look at other programmers' code and read it to make sure it is easy to read, to make sure it doesn't make mistake, okay, even visually, without actually executing the code. So that is the kind of static validation. But we can also have dynamic validation or software testing. Then in that case, we actually run the software to see it gives us the results we want. Okay, so unit testing, integration testing, and acceptance testing all requires a dynamic validation. So in the end, we hope to see the users happy with the operational system. Project management is a very important part of a software development project. And we control and administer different things. The word control, it means we check the progress of things and make sure it's progressing right. And if it's not, then we need to make some adjustment. For example, if the project is behind schedule, then maybe we'll do some adjustment by perhaps bringing in more people. So that is the control function of project management. So we monitor the progress and we make adjustment as necessary to take action to correct the situation. And project management activities include effort estimation. It is a very difficult thing to do, but we'll learn it in this course. We'll try to estimate, once we have some requirements, we estimate how much it costs, how much time it takes, how many people it takes, and so on. Then we can plan how many people need at what time, so that is planning and scheduling. And we risk there may be certain things that happen that would cause something to fail to keep up with the schedule, fail to deliver a product that works the way we want it to. And we want to identify risk, and then we will manage it so that it either reduce the chance of the risk happening, or if it happens, the impact will not be so bad. So it will have less damage if the risk ever happen. Okay? And project administration is about monitoring things and making adjustment, or perhaps keeping track of time spent by programmers on different things. Those are project administration. And in the end, we want to be able to deliver the product on time and within budget. So we don't want, but overrun project cost is a very common problem. It is related to poor software effort estimation, or it could be just a poor choice of software process. We'll talk about all those things later. OOSE, Object-Oriented Software Engineering. We try to see things as a bunch of objects in the last 2-3 decades, it has proven to be a very effective software development method. And so we use OO methodologies and modeling languages. Like the old-fashioned languages like C may not support OO very well. So that's why we have a language called C++. And some O modeling language may not support OO. Some, for example, data flow diagram may not support OO very well. So that's why we have a new modeling language, but not so new anymore. Like it's at least 20 years old. I think roughly 20 years old. UML has OO in it, so we would use something like that. So software tools is very important that we will use tools, appropriate tools. This slide compares the difference between computer science and software engineering. Computer science may try to find the optimal solutions, best solution, ideal solution. But software engineering is very practical. If we meet our standard, then we may just stop there. Okay? And computer science does not deal directly with money, but software engineering, we're about productivity, quality, and what's the C? Cost and time to market. Okay. So those are very practical things to consider. Computer science, we write small program, okay? And software engineering, we worry about huge programs. Computer science deal with technical issues. The software engineering, we deal with all issues, and most notably, people issue, because is making a team of people working together is a complicated thing. Okay? Maybe some people do not like other people, or some people may not have certain skills, communication skills, technical skills, or training. Those are all people issues that we need to deal with in software engineering. In computer science, we may imagine some simple problems to solve. They may not be real problems, so we try to imagine some sort of fictitious problems to solve. But software engineering, we cannot choose the kind of problem to solve. If we have a real problem, then we need to solve it. Okay, so wicked means like very bad problems that we need to deal with. But computer scientists just choose the problem that they like to solve. And you can say computer science is the foundation of software engineering. At the end of each chapter, there are exercises. And for this chapter, I think the question 1.2 and 1.5 is more interesting. So if you have time, after you have done the 1-page, 2-page document that I asked you to do in week 1, part 1 video, then if you have time left, you can think about 1.2 and 1.5 questions at the end of chapter 1. Okay, and we will discuss it if we have time. After discussing randomly selected student answer for the 1-page, 2-page documents. So you may remember that you did a 1-page, 2-page document to introduce yourself and also to discuss a project idea that you may have. Okay, that is what the your work before coming to the first lecture. Okay? I would discuss it in the lecture, and after my discussion, maybe you want to revise your work. Okay? And after revision, you can print out the 1 sheet or 2 sheet of paper and bring it to the tutorials, and then with that you're using it as your CV to find partners, find team members. Okay, so you can find team members with similar project topic as yours. Okay, with complementary skills, meaning if you're not good at programming, then maybe you want to team up with someone with good programming. Or if you're good at programming but not good at writing documents, writing English, then maybe you want to find a partner with good writing skills. Of course, you always want to find people who are hardworking. So based on the quality of the 1 or 2 sheets of work for week 1, you can have a good idea who is hardworking and who is not, and who is capable and who is not. So this way, it gives you some basic information of who would be a good team members. So good luck, and if you haven't done your 1-page, 2-page work, uh, please do so and submit it before Monday, 9 a.m. before the first class. Thank you.